Hello everybody, I hope you're doing well. Welcome back to another video in our introductory calculus playlist. So in the previous two videos, we've gone over the concept of special limits and kind of derived the value of the limits for some special expressions. So in the previous two videos, just as a recap, we have shown that the limit as x approaches 0 of sine of x over x approaches 1, the limit as x approaches 0 of cosine of x minus 1 over x approaches 0, and the limit as x approaches infinity of the quantity 1 plus 1 over x, all raised to the x, approaches e. So today in this video, we're going to be applying these three special limit formulations and solving various similar looking problems so that you guys get a feel for how these special limits are used within calculus. So below on the screen, you will see a link to the practice problems. I highly recommend that you go to that link and access the PDF document and follow along. In order to maximize your learning experience from this video, I recommend solving the problems first yourself and then resuming the video to see how I solve them. And I'm also thinking of, making this video into 2 or 3 parts so that I don't inundate you guys with too many practice problems, and you also can have a better experience with letting the concepts marinate. So with that being said, let's dive right in. So the first problem we're going to solve is, um, sorry, okay, we're going to solve for the limit as x approaches 0 of sine of 3x over x. So the first thing we want to do when we have these special limit problems is seeing which special limit do we know is something we can kind of match up to, right? So we see we have a sine over an x, right? What special limit from these three match that form the best? And clearly this first special limit is what matches the form the best. So if we look at the first special limit, we're taking the sine of x and then dividing it by x, right? So this x inside the sign needs to match up with this x on the denominator. So we have to make that happen in order to be able to use the special limit to our advantage. Now let's look at this problem. We see that we're taking the sine of 3x, but our denominator is just a single x. So you might be asking, Karthik, wouldn't it be great if we can just make a 3x magically appear in the denominator and then all our problems are solved? And to that, I say kudos to you for recognizing that, and that's exactly the approach we're going to take in this problem. So we have to somehow make a 3x appear in the denominator for this limit to be solved, right? But we don't want to change the value, right? So what we can do is we can make a 3x appear in the denominator, but then you have to also multiply the numerator by 3 so that you don't change the value. So at the end of the day, right, this limit is simply equal to the limit as x approaches 0 of 3 sine 3x over 3x. Notice that the first expression, right, this expression right here is equivalent to this expression. We just multiplied a 3 on the top and the bottom, so we're not changing the value. But now we know that this 3 here is viewed as a constant multiplier, so we can pull it out, right? So this is going to be equal to 3 times the limit as x approaches 0 of sine of 3x over 3x. And now we have a 3x here and then inside the sign and then a 3x on the denominator. So we're in a good form, right, to use a special limit. If you want to be even more convinced why I can do that, right, think about it this way. Let's let u equal to 3x, right? So when x approaches 0, u is approaching 0. So we can rewrite this problem as 3 times the limit as u approaches 0 of sine of u over u. And now you know sine of u over u matches with this form right here, right? Because both u is approaching 0 and x is approaching 0. So you know that this limit right here is going to approach 1, and then we have to multiply that by 3. So the answer we get is 3. So this technique of what we're doing is called change of variable, or more simply put, substitution. And this technique will come in handy with these special limit prompts. If you feel confused right now, I totally get it. We'll do some more problems along this area so that the concept will marinate. So hang in there and you will start picking up the pattern as we go through more examples. All right, cool. Let's go to the second problem. So we want to solve this problem right here. The limit as x approaches 0 of x over sine of x over 2. All right, so we want to solve this. And now we want to see which special limit kind of matches up with that form. So if we move up to our special limit definitions, we see that we have an x here and then a sign in the denominator, right? Well, This form here clearly is the closest, right? Because we have a sine and an x, and a numerator and a denominator, right? So we're going to have to use this special limit. But you might be like, well, Karthik, I have an x in the numerator, but then a sine in the denominator. But this special limit is the opposite. So can we just kind of flip this in a way without changing the value? And to that, I say, right on. Okay, cool. So now that we have that established, we have to rewrite this. We want to rewrite this problem into a form that will make our life easier. So this will be equal to the limit as x approaches 0 of 1 over sine of x over 2 over x. And now you see, right, this fraction here is equivalent to this fraction here. Take a moment to see why and verify that for yourself. But now that we have this fraction, right, we can use the quotient property of limits, and this is just simply equal to the limit as x approaches 0 of 1 over the limit as x approaches 0 of sine of x over 2 over x. And now we can just solve for the numerator limit and the denominator limit very easily, because we know that the limit as x approaches 0 of 1 is just simply 1 because it's just a horizontal line, right? Now we have to solve for this limit right here, right? So I will make some room here. So we want to solve for the limit as x approaches 0 of sine of x over 2 over x, right? And you might be like, hey, wait a second, Karthik. This problem that we solved in the previous problem seems similar to this problem, right? So we can just, use a similar trick, right? And to that I say yes. So we make an x over 2 magically appear in the denominator, and then we have to multiply the numerator by the same value, right? Such that we don't change the value. And what I would do is I would multiply both the top and the bottom by 1/2 so that we're not changing the value. And now you get the limit as x approaches 0 of 1/2 sine of x over 2 over x over 2. And then we can make a substitution, right? And let u equal to x over 2, right? So letting u equal to x over 2, we realize that when x approaches 0, u approaches 0. So this form is simply equivalent to the limit as u approaches 0 of 1/2 sine of u over u. And the answer is just going to be 1/2. So now we know that the value of this limit right here is just going to be 1/2, right? As you've expected. So 1 over 1/2 is just 2. Nice. So now that we have this problem solved, you kind of are starting to see a trick with these sine over x limits, right? If you see that trick, that's really good, and you can kind of prove the general case for yourself. Um, or you can kind of start a discussion on that in the comments. I welcome that. So now that we have this problem solved, let's solve the next one, right? The next one is going to be a little bit more involved, but it'll be sort of rewarding, right? It'll kind of put these concepts that we've discussed in the past two problems together. So we want to solve for the next problem, the limit as x approaches 0 of sine of 7x over sine of 9x plus sine of 5x over x. All right, cool. So we have this addition of two fractions. So by the sum rule of limits, we can kind of separate these out, right, into two separate problems. One thing that's good when you have limits that are kind of long and complicated is separate out the limits into separate problems and solve each subproblem kind of individually, right? This will make sure that you're organizing your thoughts nicely, right? So we're going to solve for the limit as x approaches 0 of sine of 7x over sine of 9x. And then we're also going to solve for the limit as x approaches 0 of sine of 5x over x. Let's start with the second problem because that seems pretty familiar. I think you guys can kind of see, right? We can do a similar trick that we did in the past two problems to solve for this limit right here. And if you've picked up on the pattern, we know the value of this limit is going to approach 5, right? So we've already done that problem. The more interesting problem is solving this problem right here, right? Which is indeed what we're going to do. Okay, so we want to solve for the limit as x approaches 0 of sine of 7x over sine of 9x. Now, we don't have a clear... Now, this type of formulation of like a sine over another sine is a different form that we haven't come across. But one thing you'll notice is if you plug 0 in the numerator and denominator, right, you're going to get sine of 0 over sine of 0. But we know the sine of 0 is 0. So we're going to have a 0 over 0 form. But if you've caught on to the theme of the exercise, this exercise is all about special limits. So let's look at, this limit, right, and see if anything in our special limits can help us, right? We know the value of these 3 special limits, so we have to pick which one might help us, right? And it looks like the third one clearly doesn't help, right? The second one, not so much, right? We don't really have, a cosine x over an x form or a way to get to that. But the first form is all about sines, right? And we're going to have to use this form, right? So that's what we're going to do. Okay, so we have a sine of 7x over a sine of 9x, right? But we need to somehow get like sine of 7, we need to somehow get like an x in the denominator, right? For both this term and this term, right? So that we can kind of use the special limit and solve the rest of the problem. And you might be like, well, Karthik, how do we just make an x appear in both, in both the numerator and denominator of this giant expression? And one way we can do that is realize the following fact, right? We know that sine of 7x over sine over 9x is equal to sine of 7x over x multiplied by x over sine of 9x. So we know that this equivalence holds, right? So then if you want to get a form like this, right, when we rearrange these terms, right, we will realize that all we can do is divide x in both the numerator and the denominator, right? So we are going to do that actually. So I'll use orange here. So we're going to divide both the numerator and denominator by x. So this is going to be the limit as x approaches 0 of sine of 7x over x over sine of 9x over x. And now we can use the quotient property, right? And break up this fraction into its individual components. And if you look at like, the previous problems, right? We know how to solve a limit like this, right? The answer clearly from inspection is going to be 7, right? If you're still confused on how I got 7 here, try going through this problem up here, right? Go through the approach I've illustrated right here and kind of do the same thing or replicate it for this limit right here. So with that being said, right, we know that this value here is 7, and the value of this limit here is going to be 9, right? So the answer is just going to be 7 over 9. And one thing cool you might see is that, wait, 7 and 9 were in the numerator and denominator respectively. So if I have a sine of 7x over sine over 9x, and we're taking the limit as x approaches 0, maybe a trick could be like, it's going to be like the coefficient of, the numerator sign over the coefficient of the denominator sign, where the coefficient is like, what is kind of the inside coefficient they're taking the sign of, right? So you have the 7 here and this 9 here. 7 appears in the numerator, 9 appears in the denominator, and that's our answer. So that could be a cool trick, like if you're really in a rush and you want to solve this limit without doing all the work. But I think it's good to see how the limit's kind of derived so that you're not kind of memorizing. So, okay, that sounds good. So we'll move to the next problem, right? Oh, actually, I almost forgot. We've solved this limit here, which is 7 over 9, right? But we've also solved that this limit here is 5. So the real answer is going to be 7 over 9 plus 5. So this is going to be 7 ninths plus 5. So this is going to be 7 over 9 plus 45 over 9, which is going to be 52 over 9. So the actual answer to this problem is 52 over 9 because we add the 5 and the 7 over 9. All right, sweet. Let's move to the next problem. Okay, next problem we have on the docket is the limit as x approaches 0 of tangent 5x over sine of 5x. Okay, so we want to solve this limit, right? But we have a tangent in the numerator, right? But a sine in the denominator. But in our previous problem, right, we've seen like a sign in the numerator and a sign in the denominator, and we were able to solve that with confidence. So how do we kind of engineer this problem such that you have sign in both the numerator and denominator if possible? And the secret is thinking about what tangent is, right? What is tangent? Well, in the unit circle video, right, we said that tangent of x is just sine of x over cosine of x. So when we have this tangent, we can write it in terms of sines and cosines to make our life easier. And indeed, we can do that, right? So tangent of 5x over sine of 5x equals sine of 5x over cosine of 5x multiplied by 1 over sine of 5x, right? And we can cross these out, right? So this is just going to be 1 over cosine of 5x. So hence, this problem is equivalent to finding the limit as x approaches 0 of 1 over cosine of 5x. And if you plug 0 in, right, we will see that cosine of 0 is 1, and 1 over 1 is 1. So the answer here is 1. So a trick that might help to come in handy with these trigonometric limits is knowing your trig identities along with knowing the special limits so that you can kind of do the manipulations you need to get the limit, right, the original problem, into a form that will make your life a lot easier. All right, so now that we have that established, we can move to the next example. All right, we want to find the limit as x approaches 0 of tangent of 7x over 9 over x. Okay, so we know that tangent of 7x over 9, right? We have a tangent in the numerator and an x in the denominator. So we might want to think of using special limit, but let's try writing the tangent, right? In a form of sine or cosines, right? So write the tangent in terms of sines and cosines, just like we've done in the previous problem, is what our hunch would be. And let's do that, right? So we know that the tangent of 7x over 9 is sine of 7x over 9 over cosine of 7x over 9 over x, right? So this limit here is equivalent to the limit as x approaches 0 of sine of 7x over 9 over cosine of 7x over 9 over x. And if we clean this fraction up, this is going to be equivalent to the limit as x approaches 0 of sine of 7x over 9 over x multiplied by cosine of 7x over 9, right? And now what we can do is we can kind of separate this fraction out so that, because we see here we're taking a sine and then dividing by an x. And if you remember from our special limit, we have the limit as x approaches 0 of sine x over x equaling to 1, right? So I'm going to write that in yellow, right? We know limit as x approaches 0 of sine x over x equals 1. So we're going to take advantage of that, right? So what this gives us is we have the limit as x approaches 0 of sine of 7x over 9 over x multiplied by 1 over cosine 7x over 9. And we can kind of, since we have a product and we're taking the limit of a product, it's the product of the individual limits. So this is going to equal to the limit as x approaches 0 of sine of 7x over 9 over x multiplied by the limit as x approaches 0 of 1 over cosine of 7x over 9. And you'll see this first limit, right, is just going to be 7/9, right? Because think about the first problem we did, sine of 3x over x, right? You would put a 7 x over 9 in the denominator and then multiply by a 7 over 9 in the numerator so that you have 7x over 9 here and 7x over 9 here to apply this fact, right? So the value of this is going to be 7 over 9 based on the pattern we've observed in the prior problems. For this product, if we plug in 0, we're going to get a cosine of 0 in the denominator, which is going to be a 1. So this limit here is going to become a 1. And this limit right here is going to be 7/9. And we're multiplying the two, so the answer is 7/9. And you might be like, and you might notice, right? Hey, 7/9 is the coefficient of the x inside the tangent on the numerator, and there's a coefficient of 1 here in the denominator. So that could be a handy trick, right? to keep in mind. We'll see that trick come in more handy in the later problems, but I just wanted you guys to get an intuition for how we've converted this tangent in terms of sines and cosines and applied the special limit fact in tandem. All right. Next problem we're going to be doing is this one. The limit as x approaches 0 of 2x over tangent of 6x. All right, so we see that we have an x over a tangent, right? So we've solved problems where the tangent was in the numerator, but the x was in the denominator. So just like we've done before, we can kind of flip this fraction in a way that we don't change the value, but it'll make our problem a little easier, right? So we can definitely do that. Or what we can do is realize that the tangent of 6x is sine of 6x over cosine of 6x. I think both ways of doing this are fine, but in terms of doing less work and doing all the upfront manipulations, we'll take advantage of the fact that tangent of 6x is sine of 6x over cosine of 6x and kind of rearrange everything in one go. So this is going to be equal to the limit as x approaches 0 of 2x over sine of 6x over the cosine of 6x. So this is going to be equal to the limit as x approaches 0 of 2x over sine of 6x multiplied by cosine of 6x, right? So this is all equivalent, right? And now what you'll notice is we have like an x over a sine of 6x, and we've solved a similar problem in the past example, right? So we can try, breaking up the limit, right, into individual products such that we expose the known things, right, the known entities. So this limit will be equal to the limit as x approaches 0 of x over sine of 6x, right? And we're multiplying that by the limit as x approaches 0 of 2 cosine 6x. So I'm grouping this 2 with this cosine of 6x, and then isolating the x over sine of 6x, because this form is something we've seen before, right? So I'm trying to take advantage of that. So for this form, right, we know from past examples, this is going to be like 1 over sine of 6x over x. So this is equivalent to the limit as x approaches 0 of 1 over sine of 6x over x. And we know that the limit as x approaches 0 of sine of 6x over x is just going to be 6, right? And this 1 is going to be in the numerator. So the answer to this limit, right, is just 1/6, right? So this guy here is 1/6. And then we know that when we plug 0 into 2 cosine of 6x, cosine of 6x at 0 is going to be 1. And then you're multiplying by that 2, right? So this is going to become a 2. So this is going to evaluate out to 1/6 multiplied by 2, which is just going to be 1/3. And if you notice, right, you have a 2 in the numerator and a 6 in the denominator, and you have some multiple of x, right, over tangent of, some multiple of x, right? So you're taking this 2 here over 6. And through all this computation, we've seen that this 2 over 6 is really the answer to this limit. So maybe this could be a helpful trick. If you don't see that trick, don't worry about it. It's just something I like to point out if people remember limits this way the best. But it's good to go through the examples and kind of use the special limit definitions yourself to solve these problems. All right. Next problem we're going to do to wrap up part 1 of this series is this one right here. The limit as x approaches 0 of tangent 5x over tangent 10x. So we have two ways of approaching this problem. So remember how in a previous problem we had like a sine of something over a sine of another quantity in like the numerator and denominator, and the secret we did for that problem was we multiply by 1 over x in the top and the bottom. We can totally do that for this tangent problem because we've solved similar problem, right, in the past, right? So we can do that, or we can express everything in terms of sines and cosines and then, solve the problem that way. So I think in the interest of time, I will do the former approach. So we'll multiply by a 1 over x in both the numerator and denominator. So we're not really changing the value. So we have here, right, that uh, so we have that this is equal to the limit as x approaches 0 of tangent of 5x over x divided by tangent of 10x over x. And now we have to solve, these two limits individually. And you might notice, wait, this form in both the numerator and denominator look more akin to this example right here. And we saw a trick for how we got 7/9, right? So we're going to use a similar trick to kind of get the answer for this problem. So we'll see here, right? The limit as x approaches 0 of tangent of 5x over x, it's just going to be 5 over 1, right? Through the trick or the pattern we saw, right? So this numerator is going to be 5. And likewise, this denominator is going to be 10, right? Because the limit as x approaches 0 of tangent of 10x over x is going to be 10. So the answer really becomes 1/2. So it's essentially 5 over 10. And the 5 is in the numerator, 10 is in the denominator. So thus, we have solved this special limit, and it becomes 1/2 through using patterns based on previous problems we've seen. All right, so that's a wrap for part 1 of the special limit practice series. In part 2, we'll continue more special limit problems. But hopefully, like through this video, you kind of take the time to let these techniques marinate in. Practice makes perfect, as they say, and hopefully, see you in the next video. Don't forget to like and subscribe, and leave any comments.